back to the course. Today we will talk about one of the two big questions of density functional theory, namely how to calculate the density. And we will look at this problem from a more general point of view because its solution actually reveals a great strategy that you might also find in completely different contexts. So what is the problem? As you remember, the ground state density is given as an integral of the many-body ground state wave function. More generally, we know any observable actually as a functional of the many-body wave function. The observable is an integral over this wave function. But this is exactly what we do not want. We do not want the many-body wave function around. So what can we do? Well, as we have seen, the integral is a multidimensional integral. Can we suppose that most of the information is actually integrated out? Maybe we need only a part of the wave function, and so we could get away by calculating only that part. This is not a completely stupid idea. Take the example of two species with interactions. Suppose that we want to calculate the density of one of the two species. We have the many-body wave function with the coordinates of the two species. When the two species interact, we cannot separate their wave function. But when there is no interaction between two species, the wave function is simply a product. And when we take the integral to calculate the density, because of the normalization, the wave function of species 2 simply drops out. So it is enough to calculate the wave function of species 1. Of course, in general, life is not so friendly. Particles are interacting, and their wave functions cannot be separated. Take the example of electrons and ions. We have already seen it in the very first lecture. Remember, the full many-body Hamiltonian is the sum of the kinetic energy of the electrons and of the ions, of the electron-electron and ion-ion interaction terms, and of the interaction between electrons and ions, which is usually large. And indeed, we do not neglect it. Instead, we usually make the Born-Oppenheimer approximation. We make use of the fact that the mass of the ions is large, and so we neglect their kinetic energy and add their potential energy as a constant. Now we have a simpler Hamiltonian of only the electrons, but the ions have not disappeared. They make a potential, and their positions, capital Ri, just appear as parameters. So we calculate the wave function of the electrons alone in an effective potential. This is an approximation, a widely used approximation. As an outlook, if you are interested, there are ways to turn this into an exact approach where electrons move in an effective field of ions that has, in turn, feedback from the electrons. This approach is called exact factorization, and if you're interested, you can look it up in these references. But back to our problem. What have we achieved with the Born-Oppenheimer approximation? We have achieved a system of electrons in an effective potential. The wave function of the system is simpler than the full many-body wave function because it contains only the electron coordinates and ion positions are parameters. So let us now turn this into a more general question. Is it possible to replace our real material by an effective system that is much simpler and still get some observables well or even exactly? How good could such an approach be? Building effective systems is something that we do actually quite often. Also, experimentalists do it. For example, suppose you want to know what happens to us in zero gravity. Well, you can do two things. You can take a spaceship and you fly out very far in the universe until you experience zero gravity. Then you will find the answer to your question. You would, of course, also find the answer to other questions. For example, is there a little green woman living out there? But if you're interested only in the zero gravity question, you would rather build a simulation chamber. And if you have designed the chamber well, you would probably find the correct answer to your question of zero gravity. But of course, if you then ask the question, is there a little green woman living out there? The answer would definitely not be reliable. We call such an effective system an auxiliary system. If you are good in designing it, you will get the correct answer to a certain question, the one for which you have actually designed it. But the answers to questions for which you have not designed your auxiliary system can, of course, be quite wrong. Let us look at a concrete and simple example, the calculation of energy levels in a potential. Suppose you have a harmonic potential. You know, of course, the energy levels in this potential. They are equally spaced. But suppose for a moment that you do not know how to solve the harmonic problem, but that you are able to calculate energy levels in a simpler system, for example, in a box with infinite walls. The energy levels are at a distance that goes as the square. So now we ask, for example, can I take, instead of the first energy level of the harmonic potential, the first energy level of the box? It doesn't seem so, but of course you can. It is enough to tune the box by moving it up or down until the two levels match. So you made it. You have just designed your first auxiliary system. Your box is the auxiliary system. It is simpler than the real system, but it still gives you exactly the first energy level.
But
I see an objection of Georg.
But how do we know where to put the box if we don't know the final answer?
Yeah, this is unfortunately true. How you find this move, or in more general words, how to design the auxiliary system is a new question. And we will, of course, come back to it in later lectures. But let us first conclude on the general properties of the auxiliary system. In particular, the problem of the little green woman. In our example of the two potentials, suppose you do not want just the first energy level, but let's say also maybe the third ones. But your auxiliary system was not designed for this. Of course, you can change its offset to make the third levels match. But now the first levels are misaligned. What can we do? Well, we give our auxiliary system more freedom. And we change also the width of the box until both levels match. Still, now the second level and the fourth and so on are wrong, of course. And asking for them is like asking for the little green woman. It is easy to extrapolate this discussion to all kinds of problems. If you're interested, you can find more, for example, in this reference. For now, you should realize that when you're interested only in a few observables of a complicated system, it is a very interesting idea to build an auxiliary system in order to avoid solving the full problem. To do so, you have to keep in mind that according to the observables you want to describe, you should give your auxiliary system enough degrees of freedom. And once you have built and tuned it, don't trust the answers to questions for which you haven't designed it. Okay, finally, in the next lecture, we will look more specifically at the observable density.